In section 6.4, we're going to revisit the inverse trigonometric functions. Now remember the definition. If I had sine inverse of some number x, and I said that equaled y, that was equivalent to the sine of y equals x. So for example, if I had sine inverse of square root 3 over 2, we're asking what angle, if I take the sine function of it, gives me an output of square root of 3 over 2. If we go back to our chart that we've written a number of times now, we get pi over 3. Similarly, if I had the inverse cosine of negative 1/2. Well, now here's where it gets a little tricky. We might want to draw our unit circle. It's a quick reference check. Now, the cosine of pi over 3 is equal to 1/2. But I'm looking for the cosine inverse of negative 1/2. So the cosine, remember, is the x-coordinate, so we're over here. Or down here. We usually take the first one as we're moving counterclockwise around the unit circle. So if cosine of pi over 3 is positive 1/2, cosine of 2 pi over 3 over in this quadrant is going to be negative 1/2. So the inverse cosine of negative 1/2 is 2 pi over 3. And you could do this with the tangent as well. Tan inverse of 1. This is really going to be the same thing as saying, well, that's not a very clear way to state it. It's really asking, for what value are the sine and cosine equal to the same thing? It's really saying that we've got sine x over cosine x equals 1, which is going to happen when the sine and the cosine are the same value. And we know that that occurs at pi over 4. So we can use that sort of thing. Our chart from before, the notion from the last section's video about computing sine and cosine values differently depending on which quadrant we're in, and we can use that to compute the inverse trig function values of certain numbers. Where this can be really helpful is in right triangles. Maybe I need to find this angle theta, but all I've got is the sides of the triangle. Well, we know that sine of theta is opposite over hypotenuse. 10 over 50, so sine theta is 1 over 5. But these inverse functions, they allow us to undo what the trig function does. If I take the inverse sine of the sine of theta, I just get theta. So just like solving an algebraic equation, now we're solving this trigonometric equation, and I'm going to take the inverse sine of both sides of this equation, and I get theta is equal to the inverse sine of 1/5. That doesn't work out to be a terribly nice number. If you've got your calculator in degree modes, it's about 11.5 degrees. Or if your calculator's in radian mode, this is about 2.01. Or, sorry, move that decimal point. 0.201 radians. So you can use that to find these values pretty readily. It's nice to be able to apply these inverse trig functions to deal with solving trigonometric equations. The not nice part is what we ran into down here. There aren't a lot of these, other than the angles that are popping up on our chart, where we can compute these things very quickly and explicitly. But another place that I really think these are useful is sometimes you get these compositions of functions. Now here I had a sine inverse composed with sine. sometimes, and we do see this a lot in calculus, you run into expressions that look like this. Cosine of sine inverse of 3/5. Now I could compute this with a calculator. I could take the inverse sine of 3/5, I could take the cosine of that result, and I could get something that that comes out, decently. But there's a couple of different ways we can approach it, and one of them that I really like is with inverse trig functions. So if I draw this right triangle and put an angle theta there, the inverse sine of 3/5, if I say that sine inverse of 3/5 is equal to theta, then sine of theta equals 3/5. Well, that's going to mean that opposite over hypotenuse is 3/5. Now I can use the Pythagorean theorem to figure out what's going to go down here on this other side. If I call this guy x, I'm going to have x squared plus 3 squared equals 5 squared. So x squared plus 9 equals 25. X squared equals 16. X equals plus or minus 4. But we're measuring lengths, so we're going to go with x equals 4. Now I substituted, and I went sine inverse of 3/5 be equal to theta. So really what I'm asking is, what's cosine theta? Well, cosine theta I can calculate using this triangle. It's the adjacent over the hypotenuse. It's 4/5. So I can come up with that simply using properties of right triangle and the definitions of the inverse sine function. So that's a nice powerful tool that inverse trig functions give us, both for finding explicit results like this one here, or for relating to other trig functions and giving us some information about triangles.